I remain Dr. Patience Usip. You're welcome to today's live session. We'll be considering finite automata, and the finite automata will look at the transition from formal grammars, which we took that last class, regular expressions, transition diagrams. We'll be able to um, make use of transition diagrams in constructing finite automata. And we'll see the types of finite automata. We'll understand their importance and then the application of finite automata. Sit back and do well to participate in all the class activities. Thank you. Today's class is on finite automata. I remain Dr. Patience Usoroso, and my email is as in. For today, our intended learning outcome include understanding transition diagrams, understanding regular expressions, being able to construct finite automata, which includes the deterministic finite automata and the non-deterministic finite automata. We'll be able to convert from regular expressions to finite automata. And finally, we'll explain the relationships among grammar, regular expressions, transition diagrams. Regular expressions are compact notations for regular grammars. And so when we are talking about regular expression, we know that we may not have any production rule, and then we can have even one production rule, say S implying maybe epsilon, it could be empty. And one production rule might also indicate S implying an alphabet, say A. We can also have a union of two grammar, G1 and G2, which is equivalent to saying, oh, an alphabet E in grammar 1 and an alphabet F in grammar 2. We can also have a concatenation of two grammars, which will comprise of alphabets of each of those grammars, say E and A. We also can have a clean star closure for G prime, which will mean that we can generate 0 or more alphabets in that language. For instance, if we have BC star, that means we can generate a B. Note, there is no C. That means the C might be empty. And then we can generate BC, that means the star is off. So we just have AC, or BC, that means one C. We can have more than one C, 2C, 3Cs, and more, as we see in the sentences, that possible sentences to be generated from that expression. Also, we can have expression that is called a clean plus closure for a grammar, where we have one or more sentences generated from the expression. So the same way we generated for BC star, we can generate for BC plus. That means there will be nothing like B as a valid sentence, since for clean plus closure, we must have at least one or more of that alphabet that precedes the plus sign. And so we can only have BC, BCC, BCCC, and so on. So a regular grammar is a formal grammar that describes a regular language. And we can also describe same language as the regular grammar. That means regular expressions can describe the same language that a regular grammar can describe. For example, a right regular grammar given as a tuple, a four tuple n alphabet sigma s p, where n is a set of non-terminal symbols, sigma is a set of terminal symbols ABC, P consisting of the production rules, S implies AS, S implies BA, A implying epsilon, A implying CA, and S being the starting symbol. And this can describe the same language as the regular expression A star, B, C star. You can check yourself by converting the following grammar to a regular expression in this class activity. The grammar G is given by N set of non-terminal symbols consisting of SA and B and C, and then sigma being a set of terminal symbols consisting of A, B, C. And then the set of production rules are also given here with the starting symbol as S. Let's launch into our the discussion on transition diagrams. Converting patterns into flowcharts is the major task of the transition diagrams. Don't forget that what we refer to as patterns here are the same thing as the regular expressions that we've seen behind. So transition diagrams are intermediate steps in the construction of a lexical analyzer. So it is a collection of nodes or circles, which are oftentimes called states, and the edges directing from one state to another. So a state is a condition that could occur during the process of scanning the input. This is often represented on the directional arrow. Transition diagrams and finite automata. We are going to, here is a recognizer that recognizes a keyword starting from node state 9. We see that it will recognize a letter and move to state 10 and recognize any other alphabet before it either return a value as output or it goes back to node 10 and keep recognizing either a letter or a digit. And so considering this transition diagram, we will see that a transition diagram is a flowchart for an algorithm as it is used in recognizing any language. And so we can assume that the transition diagram is deterministic. That is, not more than one edge out of a given state at a time. And we can also see that certain states are accepting of final state. There's the 11th state in this transition diagram. This indicating a lexeme has been found. We also have that there is a start, the initial state is no other state than state 9. So from nowhere we start at 9. This takes us to what we call the finite automata. We have a finite automaton to be a machine that has some input and produces a respective output, or no output at all. Of course, since transition diagrams show the transition from one state to another, we see that transitions or transition diagrams are used by the finite automata. An automaton, of course, here we see it as the abstract, in an abstract sense, it is a machine that has a finite number of states and finite number of transitions. So you see, transitions uses states, and the states and the transitions combined together gives us an automaton. And then we can also note here that a finite automaton can either accept or reject at the end. So the final state can either be an accept state or a reject state. We also see that the finite automaton can be deterministic, and it can be. So when we are talking about deterministic and non-deterministic finite automaton, we are simply referring to this state where one or more transitions from a given state, and then we see that deterministic is more efficient. We see that deterministic is a 5-tuple. It consists of a finite set of state, a finite set of input symbol, a transition function, and initial or start state, a set of accept state. So we could see the difference between the similarity, the closeness between a deterministic finite automata and the grammar. Easily executable on hardware because they are quite close to real machines. That's the DFA for you. And then it requires more space. All DFAs are NFAs. On the other hand, NFAs has only 0, 1 or more transitions from a given state. And then we can see that NFAs are more powerful. It consists of epsilon transitions, which makes transition without reading a symbol. That means you can read a blank and return no input or no alphabet. We see that NFAs can give an alternative representation of regular languages. Of course, an NFA can do all that DFAs can do. It can remove redundant states and transitions. And unlike the DFAs, it requires less space. It's not all NFAs that are DFA, though all DFAs are NFA. So, applications of finite automata is seen in a particular example of our text editors, where there is need for implementing the spell checker. So we move into our class activity 2, where I will leave you with the responsibility of outlining other applications of finite automata, having known what finite automata. Thank you. See you next class.